today we are going to talk about the waves, gravitational waves, or dilaton waves as we call it, or the scalar gravity. So if you remember, we had this the scalar gravity theory, which had the following, which was described by a scalar field phi, which we call dilaton, and its equation of motion was the inversion of phi equals minus 4 pi g times t, where t is the trace of the energy momentum tensor of the matter field. And this was the generalization of the non-relativistic Poisson equation to a relativistic theory. And we discussed some of its properties. For instance, it has the right Newtonian limit. It also predicts redshift, gravitational redshift, which is some new relativistic phenomenon. We also talked about the bending of the trajectories, and in particular the bending of light, and said that this theory predicts no bending of light in the gravitational field. Now we want to discuss another prediction of this relativistic theory, which is the existence of waves. Now, as you see, this equation is a wave equation for phi, meaning that the left-hand side of this equation, if we consider this theory in vacuum, meaning that if I set the right-hand side to 0, this admits wave solutions. Right? You can consider any function f of t minus x or t plus x, and that would be a solution of this equation. These are waves that travel with the speed of light. And now what happens is that if we consider some system of masses that are moving around and they are coupled to this gravity, they are now going to emit gravitational waves or dilaton waves. In a similar way that if you consider charged particles that are moving, if we went back to theory of electrostatics, they wouldn't do anything. But once we go to the Maxwell theory, we know that there are electromagnetic waves, and these moving charges are going to emit electromagnetic waves. Similarly here, if we have moving masses, they will emit waves of phi. So if we go far away when there are no masses, we put our detectors, we will see that waves are coming from this system. And they carry away energy from the system. So if you can imagine there's a binary, or some solar system like us, masses are moving around each other. Because of this gravitational waves, energy is being carried away from the system. So the system is losing energy, and therefore it shrinks and eventually collapses due to the emission of the waves. In fact, recently we have discovered those waves in LIGO. So we have direct detection. Before the direct detection, we had indirect detection of gravitational waves by seeing that binary systems are losing energy. So there are some binary systems that have been measured very precisely, with the period have been measured very precisely, and we had observed even before LIGO that this orbit frequency is changing with time, is increasing with time, corresponding to the fact that the orbits are shrinking. So we want to understand how to calculate that say, for instance, energy loss of the system, right? Of course, the things that we observe in nature don't agree with our toy scalar gravity, they agree with GR, which is a spin 2 gravity, but the formalism is very similar. It's a bit easier here, so it's better to work it out in detail here. Okay, so the whole goal would be try to solve this equation for some generic time-dependent source, that is, we want to assume that it's going to be localized. So if I draw some space-time diagram, the idea is that I have some system. So my binary system is something, two masses that are moving around, maybe they are colliding with each other here near the origin, and we want to solve for the profile of phi far away. Of course, since it is a relativistic theory, we expect some generic features in this relativistic theory. For instance, we expect some we expect there to be some retardation, meaning that if I look at phi here, it should only have information about things that happen in the past light cone of this part. You shouldn't know about what happened later. So we are going to see that is indeed the case. Okay, so what is the general strategy to solve this equation? This is a linearized equation for phi with a source. So the general strategy is to find the Green's function for the equation. So we've solved this equation, minus t squared plus Laplacian of a Green's function, g of t and r and t prime and r prime is equal to delta 4 of, let me just call it x and x prime. So x will be, as usual, t and r. So delta 4 of x minus x prime. Once we solve the Green's function, then the solution for phi for an arbitrary source is given by, well, let's again call it just x, would be given by convoluting the Green's function with the source. So the solution would be minus 4 pi g integral of d4 x prime g of x and x prime t of x prime. Why? Because if you apply this D'Alembert operator on phi, so we apply here on this Green's function. So if I apply phi of phi box x, which is this operator, on phi, this is equal to minus 4 pi g integral d4 x prime box x acting on g of x and x prime times t of x prime. But then we use the definition of the Green's function, which is that when box acts on it, it gives a delta function. So we get d4 x prime delta of x minus x prime times t of x prime, which is minus 4 pi g t of x. So that's how the Green's function works.
Don't you need to add an homogeneous solution to that? A solution in the case of t equals 0, for example.
Oh yeah, you can always add that solution. Adding that solution corresponds to different choices of the Green's function. So yeah, I didn't mention that. We want to consider a particular kind of the Green's function, which corresponds to a particular choice for that homogeneous solution, which is called the retarded Green's function. Which means that we want a solution for phi which vanishes if there was no sources in the past. that's exactly equivalent to adding the appropriate homogeneous solution to the equation. Okay. So now how do we find the Green's function? We go to do Fourier transform. I mean, that is one way of solving it. So, oh, by the way, since this equation is translationally invariant, then it only depends on the differences of x and x prime. So this g of x and x prime is merely a function of g of x minus x prime. There is no preferred point in this equation. Therefore, only the function can only depend on the difference. So it's a function of that, and now I'm going to write this g of t, g of x and x prime, or now let me again separate. I do the following: t minus t prime and r minus r prime. I go to the momentum basis, so I write it as d3k divided by 2 pi cube e to the I k dot r minus r prime times g k of t minus t prime. Okay, so now if we plug this in the equation, or if we take the Fourier transform of this, write this equation in momentum space, we can also write the delta function in momentum space, or the delta 3 of r minus r prime in momentum space. So what we get is a minus dt squared minus k squared times gk of t minus t prime is equal to delta of t minus t prime. And this gives us, so how do we solve this? This gives us a discontinuity condition, this delta function. So it tells us that g of 0 plus, sorry, g dt of g of 0 plus minus dt of g of 0 minus has to be equal to minus 1 because of the delta function. So I just integrate this equation in a short interval near t equals t prime. When I do that, this second derivative gives me the difference between the first derivative at 0 plus and 0 minus, and the delta function gives me 1, there's the minus, and that's the minus. So I get a discontinuity for the derivative, and then the function itself has to be continuous at 0. So what is the solution? Oh, and then the general solution for this equation, if the source is turned off, is just sine and cosine. Moreover, we want to choose the retarded Green's function, meaning that when before the source is turned on, the field has to vanish. So therefore, this g has to be this gk of whatever its argument is less than 0 has to be equal to 0. And then we also have the continuity. The function itself has to be continuous at 0. So what it means, these three conditions means that the solution gk of t minus t prime is equal to minus sine k. And this k without a vector on top of it is just the norm of the vector k. So k is normal. So we have sine of k t minus t prime over k when t is larger than t prime and 0 when t is less than t prime. And it is continuous, so I can put an equality sign here. So let's see. Does it satisfy this equation? A wave from t equals t prime is proportional to sine k t minus t prime. So it does satisfy this homogeneous equation when the source is 0, right? Second derivative of sine is minus k squared times sine. So if I plug it in here, it gives 0. Then I have the discontinuity. Then I have continuity of the solution at t equals t prime because they both vanish at t equals to t prime. So the two parts are continuous. And then the derivative has a discontinuity which is exactly minus 1. Okay, so then we find, now that we found it in the momentum space, we go back to the real space. So g of t minus t prime and r minus r prime is equal to, we just do plug the solution in there, d3k. One other notation that I use is this bar here. It means this bar has the same meaning as bar in h bar. So it means divided by 2 pi q. So we plug this in here, minus sine k t minus t prime over k e to the I k dot. Let me, for simplicity, just call it t and r. We can always recover t prime and r prime because we know that it's just a function of the difference. So g of t and r. T here r. Okay, so this is a standard integral. We first do the azimuthal angle, we get 2 pi. Then we have 1 over 2 pi cube. So we get 1 over 2 pi squared. 0 to infinity, k dk, k sine kt over, no, not okay, there was a minus sign, and then we have the integral over theta, d theta sine theta from 0 to pi e to the I k r cosine theta. So this integral is e to the I k r minus e to the minus I k r divided by I k, which is twice, sorry, divided by I k r, which is twice sine kr divided by kr. So we get minus 1 over 2 pi squared r integral from 0 to infinity dk sine kt sine kr. Any questions so far? Okay, then we can write this product of signs as cosine of sum and difference. So this is minus 1 over 4 pi squared r, integral from 0 to infinity dk cosine k t minus r minus cosine k t plus r. And since cosine is even on the k2 minus k, we can write this integral 1/2 the integral from minus infinity to plus infinity. So we find d of t and r is equal to minus 1 over 4 pi squared r integral from minus infinity to plus infinity dk cosine k t minus r minus cosine k t plus r. But this is the same thing as integral of e to the I k t minus r minus e to the I k t plus r, because the difference between this e to the I k t minus r and cosine is a sign which is odd, and therefore it vanishes when I integrate.
You write 8 pi squared.
Should I write 8 pi squared?
Because you extended the domain.
Oh, sorry. Yeah. Thank you. Okay, and now this integrals of the exponentials gives us delta functions. So this first integral gives me, or let me write both of them. So I get 1 over, so the integral gives us 2 pi times the delta function. So it cancels with some of these factors, and then I get delta of t minus r minus delta of t plus r. But t plus r never becomes 0, because t and r, remember, t is t minus t prime, and we are using this retarded Green's function. So by definition, t minus t prime is positive. We are here, not there. There we get just 0. So t is t, or t minus t prime is positive, and r is the modulus of r. So again, that is positive. So this is never, this argument is never 0. Therefore, delta is always 0. And this is 0, and we get just this delta function for the retarded Green's function. Of course, there is a. So we are here. Therefore, there is actually a theta of t multiplied. This is that t is always positive. If t is negative, we just get 0. Okay, so now that we have the Green's function, it's actually very simple. It's not always so simple, but for this D'Alembert operator, it is so simple. Now I can find a solution for a generic source, as we had it before. So phi of t and r is equal to minus 4 pi g times integral So let's go back again to this notation of x's. X prime I of x is equal to minus 4 pi g for x prime, this Green's function, g of x and x prime times t of x prime. We can use the delta function to do the time integral. Now remember, when we go here, we have to let's actually write it explicitly. So I have g integral dt prime d3 r prime t of t prime and r prime, and then there is 1 over r, but this r is really r minus r prime. So it's norm of r minus r prime, and then the delta function is delta of t minus t prime minus norm of r minus r prime. So we can use the delta function to do the t prime integral, and the integral of the t prime is up to t. This is from this theta function, this retardation thing. So finally we get phi of t and r is equal to g times d3 r prime t of t minus r prime and r prime divided by the norm of r minus r. So because of this delta function, this is again not universal. I mean, what is universal is retardation, the fact that the solution here depends only on the configuration of sources in the past light cone. What is the special here is that it depends on the configuration of the sources just on the light cone, not even in the past, because of this delta function. So we integrate over the sources exactly on the light cone. So this tells us that to know phi of t and r, we should look back and add up sources with that particular integral that end up living across, say, my past life. Any questions so far? Okay, so now we want to analyze this solution a bit better and identify different regimes of this solution. So what are different regimes that we want to consider? So we want to consider a localized system, and suppose this localized system has some characteristic size and characteristic time scale. So the characteristic size we call R, characteristic time scale corresponds to the characteristic frequency omega, that also means that there is a characteristic velocity, which is over the omega r. Eventually, we want to focus on the case in which the system is non-relativistic. We see that in that regime, things simplify even further. But for now, let's just keep this general. Okay, so now, first of all, we want to look at the profile of phi far away from the system. So, r is much larger than little r. The argument of phi is much bigger than r, the size of the system. I mean, that's where we want to look at. Of course, someone can look at it somewhere else, but we are interested in the far away solution. In fact, up to here, we didn't make that assumption, so that formula is good for studying even other regimes. Anyway, we want to look at this regime. But now we can consider two different zones, which are determined by or distinguished by the relation between r and omega, and that would exist only if this v, which is omega r, is much less than 1. If it is over the 1, then there is only one zone. But if it is much less than 1, then there are two zones. There is one zone which is corresponds to omega r much less than 1, and the other one omega r much bigger than 1. Right? Notice that if this v was of order 1, meaning that if the system was relativistic, then this assumption, little r much bigger than big R, would automatically imply that we are always in this regime. But if the characteristic velocity is much smaller, then there are two zones. So what are these two zones? So let me just, so this is some distance, which is over the 1 over omega, and then there is the size of the system, which is over the r. If the system is non-relativistic, 1 over omega is much larger than r, so there will be this zone in between and this zone. So this zone is called a near zone, and this one is called the wave zone. The separation between them is sometimes called the light cylinder. So what happens is that for a non-relativistic system, if you go to the near zone, what you see, the time dependence of the potential would approximately follow the time dependence of the system, right? In a non-relativistic system, the Newtonian approximation is good, at least close to the system. So you get the instantaneous solution that you get in the Newtonian physics would be a good approximation. So that's when you are in the near zone. That's when you have an approximately instantaneous response to the motion of the masses. But as you go farther and farther, of course this cannot be exactly instantaneous. Then this is the point at which you see the finiteness of the speed of light. Of course this is a continuous process. But then in the far zone there is no notion of approximate instantaneous solution. What happens is that effectively this phi that is following the motion of the masses, it decouples and they flow away as waves. Okay, so let us first consider the near zone. So we can simplify this equation in the near zone. By approximating by dropping this retardation, so we get an approximately instantaneous solution. But notice that this this is a good approximation, because if I try to Taylor expand this, so if I consider T of T minus R prime and R prime, so you can imagine Taylor expanding this. Now, as you can see here, this time derivative is omega, and this R minus R prime, since R prime is the location of the source, so R prime is always of order R. So this R minus R prime is of order R, therefore this expansion is really an expansion in powers of omega R. So, and in the near zone, omega R is much less than 1. So that's the approximation that I'm making here in the near zone. I'm dropping omega R corrections. And then we find this instantaneous solution that you are probably familiar with from either Newtonian gravity or electrostatics. When you have the following solution: phi of t and r is t of t and r prime divided by r minus r prime. Now, since r prime is much less than r, we can expand this, and this is the multiple expansion that you are familiar with. So there will be a monopole t of t and r prime. So there will be 1 over r, the monopole, and then the higher order tensor with a tensor in the multiple expansion of the system. So what is the next? The next term is r hat times r prime over r squared, and so on. So there should be an expansion in powers of r prime over r, the usual multiple expansion that we sometimes do in either electrostatics or also in Newtonian gravity. Notice that we can be in a regime when r prime over r is much larger than omega r. So if we have a non-relativistic system, so it would make sense to keep these terms in the multiple expansion while dropping those terms. Of course, the region that what we are more interested in is the wave zone. The near zone was when omega r much less than 1, or it's really a condition on r because omega is whatever it is. So when r is much less than 1 over omega.
The integral whatever it is r prime.
Yes, thank you. Yes, this is an integral over the sources.
Can we do that? We expand this t dependent upon time and r in its Fourier component and take value for one Fourier component which corresponds to omega, and just do the analysis for that and then construct the whole solution by the process.
Yeah, sure, yeah, of course. You can. In fact, I'll probably do that now. Yeah, since it is since it depends linearly on t, the solution for phi depends linearly on t. We can expand it in a convenient basis, and then work in that basis. Yeah. Okay, so now the opposite regime, which is called the wave zone, when R is much larger than 1 over omega. So when R is much larger than 1 over omega, then this approximation is obviously not good. You don't have the instantaneous solutions. Not a good approximation. Instantaneous solution is not a good approximation. So that we should keep. But our prime over R corrections we can neglect. As you will see, eventually, for instance, we are interested in the flux of energy at infinity. We want to see how much energy is carried away by waves to infinity, and you will see that that depends on the leading term coming from this denominator, which means that we should just we can drop this R prime over R corrections. What else do we do? Let us actually do this decomposition in terms of the Fourier component. So let us expand this or T or source. Let us expand it in terms of a bunch of Fourier coefficients. The omega of R e to the minus I omega t. Now, depending on the nature of the time dependence of this source, this sum might be an integral. If I have a periodic source, then there will be a sum here. Only discrete frequencies appear in this Fourier expansion. But if the source is not periodic, then I will have a Fourier integral. I will have a continuum of frequencies. In both cases, there is a constraint on these T omegas because of the reality of the source. So remember, this T is the trace of the energy momentum tensor. It's something real. Now, when I expand it in terms of this Fourier basis, of course, these are complex, but since they have to add up into something real, there will be a condition on this T omega. And that condition, the fact that T of T and R is real, meaning that T star is equal to T, implies a constraint on the Fourier coefficients. It tells me that T of omega star has to be equal to T of minus omega. So now I want to focus on only one of these components and see what solution for phi do I get when I consider only one of them. Then the solution, the full solution for phi will be just a superposition of those, because we have a linear relation between phi and t. So the solution for one, the solution for all will be sum of the solution for individual. Okay, so therefore we are gonna look at phi omega of T and R. Only one of the solution corresponding to one of these Fourier component. D3 R prime. Here we have T omega of R prime e to the minus I omega T minus R prime divided by R minus R prime, but now I want to keep the leading term in that denominator, so here I will just have 1 over R. Also R minus R prime is R minus R hat times R prime plus terms which are of order suppressed by inverse powers of R. So the next term here is R prime is squared over R. And I guess if we are going to large values of R, we neglect those corrections. So we keep up to here. So if you plug that in here, we get, now it is an approximate solution. An approximation that is good for in the wave zone. So I can factor out some parts which do not depend on R prime. I have an overall factor of e to the minus I omega T minus R divided by R, and then an integral over the spatial profile integrated against minus I omega R hat times R prime. Notice that this part, this face here doesn't become small as I go farther and farther away. It doesn't depend on the modulus of R. It only depends on R prime and omega. So this is fixed. Its typical size is fixed by the properties of the source. So I'm not allowed to neglect it without assuming something about the properties of the source. So I should keep this face here for now. Okay, so now, so this term that we have here, there is an integral over R prime, and there is this unknown function for now, this Fourier coefficient, but this whole thing is just a function of R hat, which I call A of R hat. Right, so what does it tell us? It tells us that far away, if you look in this direction or that direction, depending on the property of the source, you will get different answers. Some modulation that is fixed or determined by this function A of R hat. But the general property of your solution is really this. It's a spherical wave that is going away with amplitudes that depends on direction.
Can I say that A also depends on omega?
Say it again.
A also depends on omega.
Oh, sure, yes, it also depends on omega. So now let us focus on this wave, and this is spherical wave. So we want to imagine that want to suppose that there are some observers living far away from that system. Say, for instance, in the realistic case, we consider some binary systems very far away from the Earth. And we are on Earth, we have our detectors, we want to measure the gravitational waves coming from the binary system. So that they will have some, if gravity was a scalar, then they would have the profile like this. So what do we see far away? We can put our coordinate system at the position that we are observing. So we are here. And let us adopt some other coordinate system. I don't know, maybe the spatial coordinates. Let me call it again x. And we are far away, say we are at point r0. Or maybe let me draw another picture. Now this is not a space-time, it's just a space. So we go far away at position r0, then there is an observer. Then this observer has his own coordinate system. So he sets the origin to be at point r0, and he wants to expand this solution of phi that we get. We want to express it in that system. So r is r0. R in those equations is r0 near this guy is r0 plus x. And we want to suppose that we are exploring this field at some distance that's much smaller than the distance to the source. So say we are on Earth, we are measuring this field on Earth. The size of the Earth is the typical distances that we measure the field. That is much smaller than the distance to the system. And we have phi, which is a phi solution, which is now g times some factor, some a omega of r hat. Now here it will be r hat 0. It depends on the direction of r, but in this region the direction of r and direction of r hat is the same, up to corrections which are negligible. Divide by r0 e to the minus I omega t minus r, and now r is the modulus of this vector. So r is the modulus of r0 plus x, and that is equal to r0 plus, again, similar thing as what we had there, and x plus order x squared over r0 that we neglect, because x is much smaller than r0. So what solution do we get? We basically get a plane wave. So phi of t and x, phi in this in the vicinity of this observer is just some coefficient phi naught times e to the minus I omega t minus, or let me, omega t minus some k hat dot x, where k hat is R0 hat and phi naught is all of these constant factors and phases. So like there is G, there is a omega R naught hat, there will be e to the minus I omega, e to the plus I omega R0 divided by R0. All of them is just a constant phase, not phase, a constant number that appears at the amplitude. So what we see in this small region is just a plane wave. This is a plane wave propagating in the direction R hat. Of course, this is nothing surprising. The waves that are coming from a point source, and you go far away in some small region, they look like plane wave, like the radiation from the sun is a plane wave here. So we have this plane wave, and we can, and things are much easier with plane waves. We can calculate, for instance, the flux of energy that is carried by this wave. Once we calculate that flux, then we can add it up for different points on this over this sphere, over the whole solid angle. When we add it up, it will give us the total flux of energy or luminosity of the source. So the first task would be to calculate the flux of a plane wave. Any questions? Okay, so if you remember this equation of motion was following from an action, and when we have an action, we can calculate everything. So to calculate the flux of energy contained in these waves of phi, we go back and look at that action. That is going to tell us what is the flux of energy in this wave. So how does the action look like? It was just a free scalar field with a particular normalization, 1 over minus 1 over 2 kappa d phi squared. And then there were interaction terms, phi coupled to matter fields. But now we are away from the matter fields. We just want to see what is the flux of energy contained in just phi waves. So we focus on the free part of the action. Then we have this nodal theorem that tells us about the energy and momentum carried in some field configuration. So we had T mu nu, and in particular T0 mu had to be thought of as the conserved four vector associated to energy conservation with a minus sign because this 0 is lower. So in particular, T00, the energy density is minus T00, and the energy flux I guess F is minus T01, but F in one direction, for instance. Or in general, flux in the ice direction would be T0I. And that we can calculate from this action, right? This T mu nu in general for that action where we know it, but in particular T0I is given by what is this? So 1 over kappa D0 phi times di of phi. Now, if we consider a plane wave like this, then for that plane wave, we get d0r equals 1 over kappa. So di of phi is, first of all, di with upper index is the same as di with lower index, because they are mostly plus signature. And di of phi will be just just a wave number. K hat I here, so di of phi, and this is a plane wave, this is minus d0 of phi times k hat I, as you can verify from here. So therefore, for energy flux for T0R, I get minus 1 over kappa k hat I times phi dot squared, and therefore for the flux we get k hat I divided by kappa times phi dot squared, where kappa is 4 pi g. So the flux of energy in ith direction is 1 over 4 pi g times phi dot squared. And of course, for this point source that we are considering, this k hat I is nothing but r hat I. It's just the direction, radial direction pointing away from the point. So now, for instance, we can calculate the luminosity once we have the flux. We have the flux at one particular direction. Now we said that this wave profile depends on the direction, right? Through this factor A, omega over half. So at different direction that we look, we get different profiles. Now what we can do, for instance, we can add up the flux of energy at different points, and that will give us the total energy that is carried away by this wave. So if we want to calculate the total energy, total luminosity, so luminosity, remember, is energy per unit time. Is erg per second. Is given by the integral over the full big sphere of this flux, energy flux. Energy flux is energy per unit time per unit area. So this is erg per second per centimeter squared. So we want to integrate it over a big area of a big sphere, that flux, and it gives us the total energy per unit time that crosses that big sphere. So we want to do that integral. So this is an integral over dr hat with d omega times r squared. This is the area element of some bigger sphere, so you should imagine bigger sphere like that. And we want to integrate over this flux. Of course, the wave vector is always perpendicular to our area element. So we have, so this k hat times the normal vector is just 1. And so therefore we have phi dot squared over 4 pi g. This is what we want to calculate to get the total flux of energy. Now you can see why we didn't need to keep any subleading term in the r prime over r expansion for our solution, because we want to calculate this in the limit that r goes to infinity, because we want to see how much energy flies away to infinity. So we are sending r to infinity. Now the solution that we have for phi at this leading order in r over r prime is r prime over r expansion is already goes as 1 over r, which means that phi dot squared goes as 1 over r squared. So that part gives us a finite answer. That's the wave solution. And then everything else which is suppressed by powers of r prime over r will die as you take this limit. Okay, so now we can actually substitute that solution, or not that solution, but the sum over. So remember, this was phi given for some particular frequency. And we said that the full solution is just a superposition of that. The important thing is that we should do the superposition before plugging it in that formula, because this formula is nonlinear, so we cannot superpose luminosities. So we have the omega r squared 1 over 4 pi g, and then the solution for phi is, so there should be sum over omega times phi dot of omega, which is g a omega of r hat divided by r e to the minus I omega t minus r, and then there is an over factor of I omega. So this minus r omega comes from taking the time derivative. Note that even though individual components in here are complex, the full phi is real because of the reality condition that we imposed before. So there is a similar reality condition holding as a consequence of that on A omega, and that guarantees that the full sum over omega is real. And therefore phi dot square is real. So yeah, as you see, as we square this 1 over r squared cancels with that. Then I can, let me keep it here, r squared. Can simplify this, so there's d omega. There's g over 4 pi integral d omega times sum over omega minus r omega over hat squared.
That's not r square. Inside the brackets will be the r.
Oh, sorry, yes. This is just r. Thanks.
The omega is lowercase omega or uppercase omega?
Oh, this was the solid angle. On the typos. So now if we remember that this A of omega is something that depends on the characteristic properties of the source, we see that this is a general formula for relating the characteristic properties of the source to the energy that is emitted. Here there was I omega I hat times R prime. So for general sources, we can use this to infer how much energy that source is losing per unit time. Next, we want to focus on a particular case, on a particular limit which is important, namely this non-relativistic limit, and see that there will be an expansion, and one can extract the dominant source of emission in that limit. And also write an expansion in powers of velocity. Yes?
What happened to the expansion?
Oh, here, nothing, it should be there. Yeah. There was also R. Any question? Okay, so now we want to do we want to again do a multiple expansion, but a different multiple expansion than the one we did before. Namely, this is a multiple expansion that is relevant for the wave solution, not for the near solution. So in general, if we take, so remember this was the solution for phi in the wave zone, far away. So it had this, the following general the structure. So we had phi of T, we have phi of T and R, and this was given by G of G times this integral D3 R prime T R. There was this retarded solution T minus. So here we had T minus R plus R hat times R prime and R prime divided by R minus R prime, but we said that we just keep the leading term. So this R minus R prime in the denominator, we just write it 1 over R and we take it out. So that was the general solution that we had before. So one thing that we can do is that we can write this in general. This is of course G over R times some function, some A of T minus R and R hat. And what we learned from there was that if we want to calculate luminosity, for instance, that would be given by integral d omega G over 4 pi integral. I'm just writing that what we did before in a slightly different way. I'm putting all of that sum over Fourier coefficients. I'm putting all of that inside this function A. Maybe just not to confuse it with that A, I call it something else. Let's call it, I don't know, phi hat. And the answer for the total luminosity is dt of this phi hat of T minus R and R hat, the square. Now we can wonder about the spherical the R hat dependence of this function, right? We could, so this is a function of T minus R and a function of R hat. We can, and remember this dependence on R hat basically determines the amplitude of wave as we look from different directions to the system. So this is the R hat dependence is a function defined on the sphere, of course, and we can expand it in terms of the the spherical harmonic. So I can have an expansion ALMs of T minus R YLMs of R hat. So this function that live on the sphere. And in general, this ALMs will be non-zero for a generic source. But what we are gonna see now is that this expansion in the spherical harmonics actually becomes an expansion in powers of velocity if we consider non-relativistic system. And why is it the case? It's because the only dependence on our hat in this solution comes from here, right? That's the only place that our hat is. So now what I can do is that I can do an expansion, a Taylor expansion of this integral in terms of for a small r hat times r prime. So I write T of T minus r plus r hat times r prime and r prime. I can Taylor expand it. So what I get is a sum over n from 0 to infinity 1 over n factorial r hat times r prime to the n dtn of t of t minus r at r prime. Right? Everyone is happy. So now let us remember we said that we want to consider a system with some characteristic time scale or characteristic frequency of order omega and characteristic size, which is this r prime over the big R. So this expansion is an expansion. So every dt is a factor of omega and every r prime is a factor of big R. This is really an expansion in powers of omega r to the n, which is the characteristic velocity of the system. So if the characteristic velocity of the system is very small, we can truncate this expansion. And on the other hand, this expansion also determines how far we go in this multiple expansion, because the else term in a spherical harmonics start getting contribution from the else term in this expansion. So for instance, if I truncate this sum at 0th order, which means that I only keep the 0th order term here, t minus r and r prime, this term has no r hat dependence, therefore it is a spherical symmetry. It only gives contribution to y0, 0, which is called the S wave. If I keep only the first and second term, then I will get contribution only to y0, 0 and y1 m. So I get contribution to the S wave and the P wave. and so on. If I go up to S order, I will get contribution to Y length up to Y of L, and not any. So therefore, for a non-relativistic system, the multiple expansion would coincide with an expansion in powers of velocity, and we can truncate it at the order that we are interested in. For instance, if I want to find the leading source of energy loss from the system, we just keep the first term, first non-zero term in this expansion. And then these terms have names. For instance, if I keep only the first term, then if I put it in here, the result will become a monopole. So there will be a monopole Q T minus R, which is given by integral d3 R prime times T of T minus R and R prime, plus some other high terms which are suppressed by powers of velocity, because as we continue in this expansion, when we project them into spherical harmonics, we have to take out the traces, so they will contribute here some extra order V square suppressed terms. So there will be order V squared corrections here. And then there will be the monopole that we define the I of T minus R. Sorry, the dipole that comes from the keeping, or is related to keeping the second term in the expansion. And then quadrupole. And so on. So this funny combination is introduced because we want to project out the S wave from this expression. So this expression only contributes to L equals 2 component here. That's why we have this subtraction. As you can see from here, if I take the trace of this, I get 0. So it has no overlap with the monopole, but therefore I should put these extra traces back in here. So those are those higher suppressed. And then if I can write my solution phi in terms of this multiple. So my phi solution, phi of T and R, is gonna be G over R times Q of T minus R plus R hat times D, sorry, not D, but D dot of T minus R plus some higher order terms. 3R hat I, R hat J minus delta Ij times Qij double dot, and so on. I think there should be some 1 over 18 here to keep track of the coefficients. So what I have done here is I just plugged in this expansion in this expression, and now I use these names to call various terms in this expansion. The time derivatives come from the fact that as I expand, I will have time derivatives. And so at nth order term, I will have nth time derivative. While these multiples are defined without time derivative.
What do you want to prove?
Oh well, I just wanted to find some expression that is useful for calculation. So I'm gonna give you a system in the next session. I'm gonna give you a system of masses, and I want to ask you what is the rate at which it is losing energy. And you want to have a practical way of calculating that loss of energy.
Like with the luminosity, right?
Right, but so you have a source.
Yeah.
Source is basically these
energy
masses
source.
that you could, if you are infinitely powerful, of course you can just calculate that source in general, that T mu nu, and you calculate this expression. But it's often easier if the system has, there is some small parameter, like for instance the system is non-relativistic, it's often easier to do the calculation using the multiple expansion, meaning that you just calculate the leading contribution to the loss. And here I'm saying that if the system is non-relativistic, the only thing that you need to do is to calculate these multiples as a function of time and plug it in here.
So the leading term would be like the multiple in this case? No.
Well, for phi, here is this is the leading term. However, when you want to calculate the luminosity, you want to take the time derivative and integrate. And it happens because of the energy conservation, or mass conservation in non-relativistic limit, that the monopole is constant to leading order.
So
So the leading term gives 0 for the luminosity. Actually, the dipole will also give 0 because of the momentum conservation. So you start from something of order of the quadrupole. But yeah, this is because if I give you a generic source, doing this integral is horrible. It's not easy to calculate this. But this is very easy to do. You can try in the next session. Like in the similar way as in electrostatic, if you have some random distribution of charges, of course you know the general formula for the potential somewhere else is a sum of superposition of potentials of individuals, but it's something that for some generic distribution you cannot immediately get a simple answer for. But the multiple expansion is invented to get you the leading contribution to this potential, which is easily calculable. Monopole, you just add up the charges. Dipole, you just multiply the charges by distances. So that's the utility of these expansions, making it easy to calculate.
Can we also use the, we will use Legendre functions in the multiple expansion? If we introduce an angle theta, then we will say that the Legendre function will cause that appear in the multiple expansion, and in the case in electrostatics.
Yeah, these are the Legendre functions. Yeah, this is the basis that we are expanding.